So let's see what this logistic is. The name logistic regression is slightly a misnomer. It is used for classification. It cannot be used for regression, okay? Though the name says regression. But there's a reason why it's called regression, not logistic classifier. The reason is, under the hood, logistic regression uses linear models, linear regression. That's the reason. It's a classification method based on a linear regression. The response variable, that is the target variable, can be binary class, defaulter, non-defaulter, diabetic, non-diabetic, or it can be multi-class classification also. I can use logistic regression for optical character recognition. I can do that. And in my personal experience, I have seen and I have also read some papers about it. When we compare models, often logistic regression comes out on the top. If not exactly on the top, at least top few, top 2 or 3, okay, for classifications. So I'm going to start by showing you binary classification, but this can be used for multi-class classification also. Given your independent variables, what is the class likely to be? That is the objective of this model. I can also use a function available in scikit-learn where instead of defining which class an observation belongs to, a test record belongs to, I can print out what is the probability that this record belongs to this class versus this class. I can even print probabilities. Okay. This particular function is nothing unique to this. It's available in all probability-based models. Predict. You remember we use predict? We just add underscore proba. This function will print out probability values. If you go for just predict, this will print out the classes. Decision tree also has this. Naïve algorithm also has this. Logistic also has this. Predict underscore proba. Let's take a hypothetical situation. Don't worry about the PPT. Let's take a situation and discuss this concept. And for that, we are going to use 3 colors. You are a data scientist, you're working in a bank, and you have been tasked with, you have been given a responsibility to build a model where the model will take certain inputs and the output of the model will be, is this person likely to default? If I give him loan, is this person likely to be a defaulter or a non-defaulter? You have to build that model, okay? So what kind of data will you need to build such models?
His salary income, his student or his history of profession.
So past history in terms of
Civil score.
Civil score, okay, civil score is an output of a model actually. So let's keep civil score aside. You'll need his age, gender, income, any past loans he has taken, any property he has, so on and so forth, so many things. Now let's assume that one of the things given to you is his income. Forget it, this is a touchy subject, so let's call it age. Okay, one of the inputs given to you is the age of the people. So you have the past data with you. The bank has given you a past data set. In the data set, you have both defaulters, non-defaulters, and one of the columns in the data set is age. You notice a pattern here. The pattern is most of the defaulters, okay, most, not all, most of the defaulters are in the lower age bracket, okay, and you also notice most of the non-defaulters are concentrated in higher age bracket. But that doesn't mean there are no non-defaulters in low age. Okay, you observe this pattern. Now, since there are 2 classes here, what we're going to do is we are going to say green class, we're going to assign a numerical value 1, red class numerical value 0. Remember, we can't work on string data types. So the target columns will be assigned numerical types. Okay. Y1 to this, Y0 to that, no reason, you can flip it also if you wish. But we assign a value 0 and 1. We don't assign any other value, we assign only 0 and 1. There is a reason for that. Okay. Now your object, yeah. Now you find that the pattern over here, as income increases, you find more greens. As income decreases, you find more reds. You have done a linear model already. So what you do is, you try to build a linear model here. So you say, let the y-axis be probability of belonging to any one of the classes, let's call it 1. The y-axis is probability of belonging to class 1. You can actually take it as probability of belonging to class 0 also if you like. The two probabilities will be inverse of each other. So you can take any one you like. Alright? So when you build a linear model, the linear model, anybody has a black pen here? Black. No, this pen. Oh, okay. Now you'll notice that as the age increases, if this is a probability, the probability of somebody being belonging to green, the probability increases linearly. Probability increases. I can represent it with linear models. If I had taken this as 0, if this was 0, then this line, how would it look? It will be reverse. That's the difference. So you can use any line. Okay. So I'm taking this as 1 for ease of explanation because you will be able to connect to what we did yesterday. So the line will look something like this. So this line, y equal to y is probability of belonging to blue class, is related to mx, x is this variable, plus c is the intercept over here. C may be 0, C may be negative. But the problem with the linear model is, linear models go to infinity, minus, plus. Probabilities have to be within 0 and 1. They can't be below 0 or above 1. So we can't use a linear model. We use another technique where we transform this line into an S-curve. This S-curve is called a sigmoid. And it is very easy to achieve this. The sigmoid is nothing but 1 by 1 plus E. E is an Euler constant we use in mathematics, minus mx plus c. So this best fit line, the best fit line which is found for you, this best fit line is fed into this transformation, this mathematical formula. The result of this transformation is this curve. Yeah, sigmoid curve, the property is it will reach 0 at infinity, it will reach 1 at infinity. That's exactly the property of a probability distribution. Now let us interpret what this formula is saying. Keep in mind we are building the model, so which means we are in training set. So in training set we already know the labels of every record, right? The algorithm gets both the input variables and the output variable, x and y. So all the labels are already known. And the labels are shown in the color over here. Are you all okay? Shall we proceed? Now, what the models, now that I got sigmoid, I'll remove this line. I'll remove this line. Okay, this is going to infinity. We don't even need this. We don't even need this. Now what this model is telling you, let's look at that. If you take this red point, look at this, if you take this red point, what the model is saying is the probability of belonging to blue class. What is the probability of this guy? Suppose we don't know the color. What is the probability of this point belonging to blue class? It's very low. which means it belongs to the red class. So the model prediction and actuals are matching here. The model prediction and the actual label, both of them are matching. Take this green one. What the model is saying is, what is the probability that this green point belongs to blue class? This is probability of blue class, right? The probability is very high. And he is actually green. So both prediction and actuals match. Right? Hey, lady, are you with me? Sure, 100%. Okay, don't get left behind. Your expressions tell me a lot of stories. I have conducted more than, I lost count, more than 250 sessions now in data science. So I built a model. You know what's coming, right? So looking at the place, the position people occupy in the class, I can guess a lot of things about the person. Believe me, we all follow patterns, and you'll be surprised. I've noticed this pattern without fail. Based on the position people occupy in the class, okay, of course, latecomers, they don't have a choice, but people who come early, okay, based on the positions they occupy, I can draw a lot of conclusions from there, inferences from there, right? So people who are feeling doubtful but are able to ask, they're not asking, I know I can identify such people. Okay. So feel free to ask, okay? All of you, please feel free to ask. Don't get left behind. I was always a backbencher. I was always a member of the backbench society. I'm not saying anything to you. Don't look at me. If you sit in all places means? I was always a backbencher, so I know more over the backbench than the front bench. But other patterns which I observed was during the sessions, right? So a deviation from our main topic of discussion, bottom line is don't hesitate to ask. Okay, feel free to ask, don't restrict. Coming back to this, are you all with me on these two discussions? Okay, now look at this point. You see a red point here, this one. What the model is saying is, as per his income, he belongs to, probability of he belonging to blue class is very high. So the model will pass him as blue. Sorry, in this case green. Green, in this case green. So what the model surface is telling you is predicting the probability of belonging to the green class. It's very high. So the model will classify him as green, but he is actually red. So model has done an error over here. Mistake. Similarly, if you look at this one, this side, the green point here, can you tell me what the model is telling you? The model is telling you the probability of him belonging to green class is very low, so he's likely to be red. But actually he's green. So the model has done an error here, a mistake. Okay? So whenever you have overlapping data sets, as in this case, in spite of the best fit line, the classification, you will find some errors. There will always be errors. These errors are called training errors. Errors in the training data. Okay? All right, no problem. Which one is -1? This is 0, this is 0, this is 1. And this axis in this particular picture, this axis is probability of belonging to class 1. Okay, that's why your S curve is coming like this. This S curve has been built out of a linear model. If you had taken this, as probability of belonging to class 0, then it would be reverse S curve. Because your curve would be like this, the line would be like that. Oh yeah, all models have problem with outliers.
So can you explain what is the reason you have taken S curve rather than the linear?
Can somebody answer that question? Why S curve?
Because the linear was going it will go to plus infinity to minus.
Hey, linear will be overfit. Who said that? What did in linear models, we don't have any boundary. They go to plus infinity, minus infinity. We don't want that. Probabilities have to be between 0 and 1. That's why they will convert into sigmoid. Sigmoid curve has that property that will always remain between 0 and 1. So we are able to map the numerical values to probability function.
So coming back to the same question, now you explain the binary thing. So same thing is applicable for the multi-class.
Yes, in multi-class classification, it will be 1 versus rest. Suppose I used this logistic regression for OCR, optical character recognition. So you'll have one S-curve for A versus others, one S-curve for B versus others, so on and so forth. So in your mathematical space, you'll have multiple S-curves cutting each other. One is for A versus others, the other one is B versus others, C versus others, so on and so forth. All these algorithms, decision tree, Naïve base, support vector machines, neural networks, logistic, they all break your mathematical space into compartments. They break them into compartments, pockets, where one pocket belongs to this object, the other pocket belongs to that object. All of them do that. You done decision tree yesterday? Yes. Which data set did you use? Diabetes data, PMA diabetes data set, okay? That is a binary classification actually. So when you make decision trees, okay, this is the structure you have of decision trees. What you're doing here is, this entire mathematical space is your root node. The entire data set, all data points put together is your root node. Then you find out one particular column on which you break the data into two. That is like putting a vertical boundary here. So these two now are these child nodes. But you have not achieved your what you call homogeneity. Your Gini index is still very high, or entropy is very high. It's still not pure leaf. So what you do is you again find a column here in this data set and break this into two. That means you're drawing a vertical boundary. So this and this is the child node here and here. So decision tree also breaks your mathematical space into pockets such that each pocket becomes homogeneous at leaf level. So right now I've reached the leaf level. Hopefully at leaf level, each pocket is become homogeneous. Now I know what are the conditions under which somebody belongs to this pocket. That is called the rules of the decision tree. All algorithms break your mathematical space into pockets, including logistic regression.
For this
You treat A as class
1 for this family, the default is
This is binary class classification. If you're in multi-class classification, optical character recognition, then you treat at one point in time all data belong to class A, alphabet A as 1, and rest of them are zeros. See what is the boundary. Then treat all the records belonging to class B as 1 and rest of them zeros. Then redraw the boundary. So you'll have multiple boundaries cutting each other.
This is like multiple variables affecting a particular attribute that we're trying to tell. For example, if a customer is fraud or not, if I'm considering age as a factor, I'm also considering gender as a factor. I'm also considering
that will be hypersurface. Hypersurface. But multiple hypersurfaces for A, for B, for C. You'll have that, right?
So will that be consolidated single mathematical space?
Yes, 100%. Yes. The whole model will be a composite of all these surfaces. Okay. Let's move on.
So multi-class is always 1 versus A, rest.
Multi-class classification, most of the algorithms give you OVR. OVR means 1 versus rest. Some algorithms give you a facility of replacing the OVR with Bayesian probabilities. Okay, you can actually go and modify that in your hyperparameters. But most of the algorithm by default will give you OVR. Right? Some algorithms like support vector machines, OVR is not very efficient, so they give you another technique called Bayesian probability based. Shall move on? Okay. It has a gradient descent algorithm working under the hood to find you the best fit line. Right? The linear model uses gradient descent algorithm. Do you remember gradient descent discussion we had yesterday? See, the gradient descent is to find best fit line. I'll quickly summarize this. I know it was too much in one day to cover. Your error function will always have this form, not very difficult, guys. If I give you equation y equal to x square, for any value of x, y will always be positive. It's a squared term. If x is -1, -1 into -1 becomes +1. This is called a convex function. So whenever you have any function raised to power 2, it will always be convex. Right now this is single dimension. This x can be multiple dimensions. So if I take 2 dimensions m and c and plot the error, this will be a bowl shape. Right? Now in this ball shape, we have to reach the global minima. It's guaranteed you will have only one global minima. You won't have any other. For quadratic error expressions, you will always have one global minima guaranteed. Okay. So we start with some random MNC. That random MNC gives us some error. The same concept applies in logistic because logistic is also a linear model. Right? From that MNC, it will come down to this using your partial derivatives. Concept, okay? There's a lot to discuss in this. I'm not going to discuss all these things at this point, but you will need this if you're going to do deep learning, neural networks and all these things. Right? At that time, we'll take it up in detail. Same concept will apply today in logistic because logistic uses linear model under the hood. So it finds for you the best fit line given the spread of the data points in mathematical space or best fit plane or a hyperplane. Once that plane is found, that plane is sent through the sigmoid transformation and it's converted to S curve. Right? Now the driving force behind this, here in this case it was quadratic. In this case, the S curve which is formed, the S curve can be shifted forward, backward, upward, downwards. Let me see if I can show this to you, okay? What happens is, insert, if I take this S curve, I hope it works. Yeah, it works, okay? Now this S curve, you can move it up by changing the C in y equal to mx plus c, or you can move it down. You can flatten it. To flatten it, what do you think we'll use? The slope, m of the line. By changing the slope, I can make it vertical or flatten or move it up and down using c. So by using these two parameters m and c, I'll find out which sigmoid surface I get is the best surface. And to find out which is the best sigmoid surface of all the infinite possibilities, it uses a function. That function is called log loss. This is just like your gradient descent, okay? Don't worry about this function, it's actually very easy. Looks dangerous, but actually it's very easy. Now let us look at the log loss function. Looks very dangerous, but it's actually simple, very simple, okay? So forget the sigma and all these things, just take the expression yi into log of pi, okay, plus then 1 minus yi into log of 1 minus yi into log of 1 minus pi, correct? Just look at this expression. What is this y? Y is the target variable. Target variable. We know the target variable ranges from 0 and 1 only. 1 is for green and 0 is for red. So this yi can take a value of 0 or 1. Okay. Now let us look at 4 situations. I'm going to show you 4 cases, and the 4 cases we're going to discuss here. Where is the 4 cases? These are the 4 cases. Look at the first case. In your data, the first test case, these are 4 test records, okay? The first test record has this income. The model is saying the probability belongs to blue class is very high and is actually blue class. No error, 0 error. right? Zero error. Come to this. What is the y value for blue class? 1 into what is the probability? Very high, almost close to 1. Log of a very high number, when log comes close to 1, this is 0. Log of a very high number is 0, close to 0. 2 raised to power 0 is 1. So this is log to the base 2. Okay? So log to the base 2 of a very high number means close to 1, will always be 0. Come to this term. This becomes 1 minus 1. We don't even need to evaluate because this is 0. So when you do correct classification for the blue points, your error is 0. Let's take the next case. The next case is this red point. Let's take this red point. Let's take the case number 3. Or let's take case number 2, the second case. Okay? As per the model, given his income, the probability of him belonging to blue class is very low. Which means the model is predicting that he belongs to the red class. As per the income group of this person, the model is a blue line. It's saying probability of him belonging to blue class is very low. Anything below 0.5 is very low. So the model is predicting that this guy is going to be red, but actually he is blue. So let's see what the equation says. He is blue, value is 1. Probability is very low that he belongs to blue class. The model is saying probability is very low. Log of a very small number is a very large number. So this is into a large number. Okay? Since he is a blue class, this expression we don't even need to evaluate. It will be 0. So whenever you do misclassification of the blue, you get a very large error. All right? So the more the blue class is on this side, larger the error will become. So in technical parlance, what we say is, more confident this algorithm is about a particular classification, which we know is wrong, more the error it does. Right?
So if the probability is less, because in this PI will be, if it goes lesser, then the larger it becomes more large.
Yeah, correct.
The error will go more. If you go down, it will still further.
So for this blue point, where the probability of him belonging to blue class is almost 0, this error will be very high.
So what we are saying is more error we do on this side.
For blue class.
For blue class, then loss is more.
Yeah, exactly.
And upper side, even the error is there, but loss is less.
We'll come to that. We'll first discuss only the blue class. The more blue points are on this side, in this case, the more the errors will come out. Larger the error will be. Okay? Now look at this, the red one, the fourth one. Or let's take the third one. We know that this guy is a defaulter. The class is red. The model is given the income, the model is predicting he's going to be defaulter. Come to this equation. What is the label value for this guy? Class red, 0. So this expression becomes 0. We don't even need to evaluate. Come to this guy. 1 minus 0 is 1 into log of a very, very small number. Number minus 1 becomes almost 1. So this expression turns out to be 0. Log of a very large number, okay, is 0. So this expression comes too close to 0. For red classification, we use this part of the equation. For blue classification, we use this part of the equation. Take the last case where the red class is misclassified. The model is saying he belongs to blue class.
So one question. So PI is the probability, right?
Of belonging to blue class.
Belonging to blue class. That's why it is 0.
Yeah. See, the model, the surface is probability of belonging to blue class.
Okay. That's why it is 0.
Yeah, exactly.
For the right.
Exactly. Look at the last case. Last case is the fourth case, where the fourth case is misclassification of red. So when you do misclassification of red, this expression is not for red, so forget it. Come to this. This is 1 minus 0 into log to the base 2. This is a very high probability which your model is predicting. So this becomes a very small number. Log of a small number is a very large number. So error is very large. That's all this equation is. So you sum up the errors done across all the data points, those which are correctly classified, those which are not correctly classified, sum it up, you will get the total error across the entire model. Sum of squared errors, same way this. So the objective is to minimize the sum of squared errors by finding the right logistic surface given the classes.
And so the gradient distribution will say that. So suppose it's a high loss, and it will go in a direction where it want to reduce that loss.
Reduce the total loss. Correct. Yesterday, the sum of squared errors was driving the gradient descent. Here, this will drive the gradient descent.
So it does gradient descent first to get the linear equation and then does the second to get the right
Sigmoid curve. Both happen together actually, both happen together. It's not one after the other, both happen together simultaneously.
What is the range for this plot? Between to the data.
0 and 1. All 100% is your complete loss. Which will happen when you have all the red 7 classified as blue and all the blue 7 classified as red.
This sheet always places 0.
Yeah, for classification, always 0. All right, shall we move on? Extension of linear model that we saw yesterday. The beauty of logistic regression is it makes no assumption about the distribution of classes in the feature space. Many of these algorithms, linear model especially, if you're building linear classifiers or linear regression, they expect Gaussian distributions. You understand the term Gaussian distribution, all of you? No? Okay. When you build any model, expectation is if you take this attribute, the data will be spread around the central value of this attribute with some standard deviations. Same way, this attribute will have a distribution with standard deviations. When you plot this together in the mathematical space, they will look like, if they are independent of each other, they will look like this. We already discussed this. This kind of a distribution is called Gaussian. So in 3D, it looks like a bell curve. All right. This algorithm does not make any such assumptions, but keep in mind, if you have outliers in your data set, even this algorithm will fall on its face because it is based on linear model. So those outliers have to be addressed. What will happen if you have outliers? If you have outliers, you're likely to have outliers for, say, for example, what do you call them? The class 1. If you have an extreme outlier here, then you're in trouble. If you have outlier on this side, no problem. If you have outlier on this side, you have a problem. So more extreme it is, more severe the outliers is, more the errors will be. Right? Okay. You can do multi-class classification using either binomial distribution in this case or multinomial distribution also is possible. You can also print out the probability values if you're not interested in the class, but I want the probability values. What is the probability it belongs to this class or that class? Quick to learn because it's based on linear model, and you have gradient descent to help us out to find the best fit line quickly. Fast in your test data also. In test data also it's very fast. And as I said, many times I have personally seen logistic regression stands out among the top few in many of the situations. Resistant to overfitting, because as a simple linear model, linear models cannot be very complex shapes. It is resistant to overfitting. Okay. Resistant to overfitting does not mean resistant to bias errors. It means resistant to variance errors, right? But we have another one to deal with. And you can print out the coefficients, the probability values, and interpret the probability values. So the model is not a black box, right? Disadvantage in classifications is it uses linear boundaries. What it means is, if the distribution of the classes is something like this, then the model will suffer. Right now we took a linearly separable this thing, but what if the distribution is not linearly separable? Then logistic regression will suffer. If the distribution was like this with overlap, but it was like this, then it will do well. But if the distribution like this on the attribute you have decided, you see the difference? The difference is, if I plot the density graph, okay, in this case, the two density curves are overlapping. Your t-test, analysis of variance, and all these things will tell you that this record belongs to this class, that class, 50-50. It will not be able to classify. On the other hand, if I look at this situation, your overlap is there, but the central values are shifted apart. So when we have distributions which are linearly separable, may not be 100%, then logistic will do well. But you have distributions like this. I don't know whether you noticed, PIMA dataset is like this. That is why in PIMA dataset, you will not be able to get accuracy beyond 70%, 76%. Do whatever you can, right? So, it will not give you beyond 75. When the data distribution is like this, none of the algorithms will be able to help you out.
When we start building this model, we need to check what our data distribution is like.
100% you have to know your data before you start building the models. You have to know your data, which means you have to know every attribute, how the data is distributed, if you're in classification, how the classes are distributed, which dimensions or which attributes are able to linearly separate the two classes. Use only those for your classification models. You have some attribute where both the classes are significantly overlapping, including the central values. Using such attributes for building model is useless, and PIMA Indians, you will see all the dimensions are like that.
So then what we can do actually? We can't do anything. No other algorithm.
No algorithm. Okay. What human brain cannot do, an algorithm cannot do. So you have to have at least one attribute, as you will notice in another data set that is called bank.csv. There also the data overlaps on all the dimensions between the two classes, but there are few dimensions, 2 or 3, where the data central values are separated apart. Based on this 3, it gives you 96% accuracy.
So for our model, we should consider only those.
Only those, yeah, correct. You don't need to include all of it.
What is the name of that bank.csv, that two attributes? What in the data?
Some attributes, I'm just randomly taking.
What is that term called? Gross error?
This is scatter plot. This is scatter plot. Now you find out how the density of the plot changes when you move from this direction to this direction. You will see that the density is very low, very low, very low, increases very high, highest, then it starts falling. So when you convert this into 3D, it becomes a normal distribution. In 3D, this becomes a normal. That is called density function. 3D.
So can we switch the axis for analysis in this case?
Can be.
Can't we switch the axis for analysis?
Switch means?
Say y-axis becomes x-axis so that your distribution.
What you're basically saying is, no, I'm comparing these two with this over here. This axis is not there. I'm just saying, if you have a distribution like this, your logistic will do well. If you have a distribution like this, your logistic will suffer. Any algorithm will suffer. Okay? But what you're saying is, can't we switch to this axis where the two classes are separated out? That's what you should be doing. So if you have two axes, two attributes, on one attribute they are not linearly separable at all, but on the other attribute they are linearly separable, use the other one. That's what I'm saying. Yeah, all right.
in 2-dimensional frequency like this, we can change to 3-dimensional. We can see some of the data are up. Some of
So
the
use
data.
that dimension, which is helping you to separate out the two. Don't use this dimension.
Can we apply one model on one attribute and another attribute?
That is very confusing question.
That is what random forest does. Random forest, every node of the forest is constructed using randomly selected features from the data set. Yeah, it internally does that. But random forest is the only one which comes close to what you're asking. No, it doesn't do that. It randomly picks up. It doesn't see whether these are the best attributes. All right. Okay, let's move. Let's do a hands-on. This is the same data set. Pima Indians diabetes data set. Same data set. Shall we do a hands-on on this? Okay. All right, guys, are you all ready? Okay. So if you have access to the code, the first line is matplotlib. We already know what it means. I'm importing from scikit-learn linear model logistic regression. Yesterday we had imported linear regression. Okay. Then I'm importing matplot, SPLT, Seaborn. I use Seaborn libraries for my plots. Especially pair plot comes out very well in this. So I'm going to use this. Train test split, you already know what it is. Numerical Python. And to measure the accuracy of the model, I'm going to use metrics. So whenever you're doing classification, one of the most important tools for evaluating a model is your confusion matrix. Okay, so that comes through this metrics library. We'll see all these things down the line. Earlier, this Pima diabetes used to be available in UCI dataset, but now I think it has been removed or archived. So it's not available, but I downloaded it from kaggle.com, another site. I'm loading the dataset over here. It's a data file, it's a text file. While loading the data file, I'm feeding the column names here, which I got from the original source, the column names. So the column names are, the first column name is pregnancy, how many times, by the way, this particular test was done amongst Pima tribes, a tribe in South America, where apparently the ladies are prone to type 2 diabetes very early in age. So this research was done by this university where the objective was, can we build a model and predict who is going to have type 2 diabetes by the teenage? Okay, for that they did research on that community. Some of them were diabetic, some of them were not diabetic, and the characteristics that were captured are these. The first one is number of times pregnancy reported by the subject. The next one is plasma level in your body. Plasma is a component of the blood. Then we have blood pressure. This is diastolic blood pressure. This one is diastolic blood pressure. Then we have skin, where apparently people suffering from type 2 diabetes in that tribe, they have some kind of skin folds. This is measurement of that. Then they do some testing. This is called fasting sugar test or something. That is this test. Body mass index. PEDI is another test. Some pedigree test they do, I think. It's another test related to blood sugar. Age. And the last one is your target column, whether this person was diabetic or non-diabetic. Diabetic means 1, non-diabetic is 0. Now the whole thing, that the objective is, we are trying to find out, is there a relationship between the independent variables and the target variable? What is that relationship we are trying to find out? That relationship we assume exists in the universe, in the real world. We are trying to find out whether we can discover that relationship. So for that, we are building this model. And I always do this based on the experience on car MPG dataset. When you look for this head, okay, when you look for some sample records, you see all numerical values. But what is a guarantee that there is no record further down which has some non-numerical values sitting in the numerical columns? What is the guarantee? How do you identify that? To identify that, we can use this method. What I'm doing is I'm using a numerical Python function isReal. This function is a binary function. It's a Boolean function. It will give true or false. This function, I'm applying it onto, look at this apply. I'm applying it onto all the rows, all the columns of this. This is the beauty of Python, where you have to do minimal coding. If you had to do this in Java, you'll probably write a for next within a for next over here. So all that thing is taken care of. So what's happening is I'm going to apply this function isReal on all the rows, all the columns of PMADF. Okay, and you see this tilde over here. This is a not operation. I want only those records where it returns a false. Okay, fortunately there are no records where it returns a false, which means all records, all columns are numericals. What is the other way of finding out whether any such non-numerical characters have come into the data?
Data types.
Def types, that's it. Def types, when you do, it will return the data types of all the columns. If there is any non-numerical value in any of these columns, it will return it as object. That is easier than this, def types.
So what we do if there is a non-numerical?
What we do if there is a, we have to go and identify the record, convert that into NA, NaN, numerical. Then you can replace with median, mean, whatever replacement strategy. We don't have any such case right now. Okay, but we have nothing to be happy about because we're seeing a lot of zeros. And zeros in blood pressure is surprising. It can't be, not possible. Zero in plasma is not possible. But you have zero values in blood pressure, you have zero values in plasma. So missing values are there. The missing values will cause problems. We need to address the missing values. Okay, let's move on. Do a describe how the data is distributed on the various dimensions. Univariate analysis. If you don't like this, don't do it. Do the pair plot. Pair plot also gives you visually the same univariate analysis. Okay. So I'll quickly tell you one. Look at the difference between, for the test data, the test attribute, look at the difference between the mean, 80, almost 80, and the median, 30. The mean is drastically shifted away from the median on the higher side, which means there is going to be some long tails on the right side, on the higher side. Mean gets easily impacted by outliers. So some outlier is pulling mean towards the right side. How do you confirm that? Look at the distance between the third quartile and this. Look at this. Correct. Look at, you're like me, you don't want to calculate? Can you tell me how long is long? The right side tail, look at the length and compare that to the left side tail. Left side there is no tail. 719 units. So is this possible or is this a typo? We need to go and check. Maybe this is a typo. We don't know. Okay, right, I'm going to move on. The next thing that you have to do is first understand how the data is distributed on your various dimensions. If you think there are outliers, we need to address outliers. We already know we have missing values, we need to address missing values. The next thing you need to do is, since you're in classification, how many records are available for each class in the data set? Look at that. The number of cases for non-diabetic, 0, is 500, whereas the number of cases for diabetic is half of that, almost half. You're preparing for your board exams, and most of the questions that you solve, practice on, is calculus. A small part you do it on trigonometry. Obviously you're going to flunk in trigonometry, right? Why? Because the pattern of questions that come to you in the exams in trigonometry may not have been reflected by the patterns that you have used, which means you have not gone through all the possible patterns in the trigonometry questions. Same thing will happen here. to the model, I have given only 268 of the diabetic cases. Maybe this 268 does not reflect all possible permutations that lead to diabetes. So the model will perform poorly in predicting the diabetic cases. It will perform relatively well in predicting the non-diabetic cases, but I want the reverse. The objective is the reverse. Okay? And keep in mind, whenever you're in classification and the classes are skewed like this, all algorithms are biased towards the higher represented class. All models, the objective is to minimize the overall misclassification. So their focus will be on the higher class. So this is another source of bias which comes into the model where the algorithms themselves are biased. So how do you handle this? Make find it too? Yeah. We call this strategy upsampling, downsampling. Okay, there is a strategy called upsampling, downsampling, which I'll refer to, which I'll take you through when we do FMT, model tuning, but right now we're not going to do that. There is a package available, it's called InBlearn, but right now we're going to live with this. There's another way of improving the the classification, performing better in the underrepresented class, that is called modifying thresholds. Thresholds. In logistic regression, Naïve based, any other probability based model, the cutoff is 50%. If the probability of belonging to blue class is 51%, the data point will be classified as blue. If the probability of belonging to the blue class is 49%, the data point will be classified as red. So the boundary is at 50%. Okay, I can modify the boundary. Though none of the algorithms allow me to modify the boundary directly, I can build wrapper class around the algorithms. I build the model. Around the model, I write my own class where I modify the threshold. Okay. Once again, I'll cover this in FMT, not now. It'll be too much. So we can play around with the threshold, modify the thresholds to improve the accuracy of the underrepresented class. We can do that. Okay. How do we do that? We'll take it later. But whenever you see in classification skewed distributions like this, be ready. There's no way you can achieve a very high accuracy for the underrepresented class unless you play around with these two techniques. Let's move on. So this is my pair plot. Okay, I don't like this. So let me quickly redo this. All right, I'm going to come into, I'm not going to do all this, I'm going to come straight to this where I'm going to say SNS pair plot, comma, dag underscore kind is equal to KDE, kernel density estimate. Since these are numerical values, it makes sense to have this. And hue means color, is equal to the last one, what we call it, target class. So hue is equal to class.
So you haven't treated outliers
Not
or
yet.
the zero values.
Not
So you just
Yeah, on the raw data. It'll take some time. It's fast actually. Yeah, there you go. Now let us understand this pair plot. All of you have it? Let's look at the very first dimension. The first dimension here is pregnancy reported. Okay. The blue is non-diabetic class and the red one is the diabetic class. The orange is the diabetic class. Okay. If you look at it, the two distributions are overlapping with the central values. They are overlapping. Very small separation over here. Come to the next dimension. The next dimension is your plasma. Plasma, you see long tails on the left side with a small bump. This is their outliers, the zero values. But otherwise, both the classes, the blue class is perfectly, looks like almost like your normal curve. And the central values are overlapping. The central values are eclipsed. So once again, not a very good attribute, but at least we have some differentiator here. Look at this one. Even the outliers are overlapping. This is your blood pressure. These are the zero blood pressure cases. They are also overlapping. Yeah. So there is no way your blood pressure will be able to separate out. Based on blood pressure, you cannot distinguish diabetic versus non-diabetic. There's no way you can.
No, but if you correct those zero values,
Still, whatever technique you apply will be same technique. So both of them will shift together, right? So we have a problem there. Look at the next one. This is even more surprising. Almost gone. Skin color, not skin color. This is skin fold. Yeah, you see the same problem here also. Every dimension you look at it, every dimension has this problem. On none of the dimensions, except for a few dimensions where you see small difference in the two classes, none of the dimensions are separating the two classes out. So even you put all these dimensions together and build a model, we are not going to have anything. Yeah, it's overlap, almost this case, the previous case, this one. And that's what we are seeing here. The two classes are overlapping on every day. They are not shifted like this. Let's go ahead and build a model. Let's not be very hopeful about this. Any model will give a problem here. So what I'm doing here is, this is not required. It's not required to be done. All algorithms can take as input the data frame itself. But earlier I used to do this as a practice, where I'm converting the data frame into an array. So data frame minus the column headers is called an array. Okay. And that array, I'm taking the independent attributes into X and dependent attribute in Y. And then I'm splitting this X and Y into train set, test set. Is this part okay with you people? All of you with me on this? All of you, Sairam? You're also on this? Great. Now look at this. I'm instantiating the logistic regression model. You can call it anything you like. I'm calling it model. I'm doing the fit. This is where the best fit line is found and convert into your sigmoid curve. The fit. Once the model has been found, then I make use of the predict function of that object on test. So these are my predicted labels, diabetic, non-diabetic. The actual labels are Y test. Okay. Some people get confused here, so I'm going to stop it. Don't look beyond this. Just stop here. I'm asking you to just look at this part. Till this point, everything is fine? Okay. Now what I can do down is, I can, for the time being, I'll remove this. Okay. I'll put a, yeah. For the time being, just ignore this. Control X. We'll put it over here. Insert cell below, and we'll put it here. All right. I'll uncommit it later. I'll do that. Okay. Now look at this. Have you seen confusion matrix before? Yeah. All of you agree it's exactly what it's called? It confuses people a lot, right? Confusion matrix. So what I do is, as a practice, when I make my confusion matrix, I always keep the actuals on this side. Actual diabetic, non-diabetic. And the predicted, the output of the model on this side. Diabetic, non-diabetic. This is my practice. You can follow the other way, but whichever way you follow only one. How do you control this? Since again Y test first, this is actual, it goes to the rows, Y predict next, this is your predicted values goes into the columns. If you flip this, you'll flip that. Now what it's saying is, of the 147 diabetic cases in your, sorry, this is non-diabetic, not diabetic, this is ND, non-diabetic, this is diabetic, ND, D. Awfully sorry. If you go and read the source of the data, they're very clearly told 0 is non-diabetic, 1 is diabetic. Of the 147 non-diabetic in your test data, 132 have been classified as non-diabetic. No mistakes. For this class, true positives. Of the 147, 15 have been identified as diabetic. Incorrect classification. These are those values of red lying on the extreme end, values of blue lying on the extreme end. Look at the diabetic class. A84, there are 84 diabetic cases in your test data. Of this 84, 46 have been correctly classified as diabetic. 84 minus 46 is 38. 38 have been misclassified. Okay? Now look at this. Now look at this. What is the overall accuracy? 77%. Looks decent. But let's look at accuracy in diabetic class. Okay? We call it recall. Recall is, the formula for recall is true positives by true positives plus false negatives. Looks very hi-fi, but what it means is true positives divided by row total. So the recall is 46 divided by true positives plus false negatives. This is false negatives. For this class, this is false negative, right? So yeah, so it is 46 plus 38 back to 84. That comes to around 55%. Hey. It's coming like 55, 54%, right? That is like tossing a coin, heads or tails. You don't need a model for this. Right? So to get this kind of accuracy, you don't need a model. You can just toss a coin and say diabetic, non-diabetic. That is what this is. So overall looks great, but don't get fooled by this. What is important is this, but this is what we expected because this is represented very poorly, the diabetic class. This is important for us. Look at the recall for the non-diabetic class. Non-diabetic class, the recall is 132 by 147. This will come very high, 90%, 80%, 90% roughly around. So the recall for the non-diabetic class is very high. Recall for the diabetic class is extremely poor. But that's what you should expect. We wanted the reverse. So that's what will happen when you have situations like this. Okay? There is no way you can get a very good model when the individual attributes are poor attributes and the classes are underrepresented. You can't do it. So the magic happens in the data. How do you prepare your data for analytics? That is where the magic is. It is not in the algorithms. Okay? It depends on data preparation. 80% of our project estimated effort in data science goes into preparing the data. Running the algorithm is matter. Then rest around 15 to 20% goes into fine-tuning your model. It goes into that. All right, let's do, there is a function called score. Instead of doing this, I can directly call score, but don't rely on this when you're doing classification. What this function does is, it regenerates the model and then tests it on this test data. It regenerates the model, then compares the test data and this automatically and gives it the score. Okay, so this has nothing to do with confusion matrix. You can actually run this and say remove the hash, run it. It should give you the score. Model is not defined. Why? What spelling mistake? Oh, I have not executed. I'm just showing you this. Okay. I have not executed these lines. So it gives you overall score, but overall score is not reliable, so don't depend on this. Shall we move on? You need to learn the tricks of identifying good attributes. Feature engineering, feature selection, and that is where the core lies. 100%. Domain. If I want to predict the time taken to travel from A to B, then I should have the domain experience of what are the factors that can impact the time. That's what the attributes they collected are useless attributes. It's not good attribute. I don't know, but the fact is it's not good data set for classification.
Here we see the diabetic class of all your models were biased towards
Non-diabetic.
So we cannot use synthetic data.
That is what this imlearn does. Upsampling, when you create upsamples, it actually creates synthetic data out of the underrepresented class.
Is it a acceptable practice to do that? Or
You have only one choice. Either accept it or stay with this. No, I'll tell you. On a serious note, it is an acceptable practice. It is an acceptable. Finally, what is important to me is the model should generalize in production. That is important to me. So when we release models into production, the models are not immediately used in production. They are put into alpha test, beta test. If after jacking up the data, if the model is performing poorly in the alpha and beta, I will not release it.
It's like pre-prod.
Yeah, it is.
Just because you don't have enough data in that's not.
It's allowed. See, I'll tell you quickly what happens in upsampling. Okay, upsampling uses k nearest neighbors. So what upsampling does is, if you have two classes, this is underrepresented class, so diabetic class, triangles, and non-diabetic, most of them will be non-diabetic, okay, and there is some overlap here, okay, most of them are non-diabetic class. What this upsampling using imlearn does is, it tries to generate synthetic data out of this. Just one thing, let me finish this. The synthetic data generated is such that it does not disturb this overlap region. It creates synthetic data in these regions. Yes?
but by doing the upsampling, are we not introducing the bias error?
100%, guaranteed.
Yeah.
So we are, by introducing the bias error, we are taking away the bias in the algorithm, which is towards the higher class. We are trying to cancel that bias error by upsampling.
So actually upsampling and downsampling is adjusting the bias.
Correct.
We are actually trading the bias.
We are trading off the bias which exists naturally in the algorithm towards higher class.
Are they exact duplicates or?
No, they are not duplicate. They are synthetic data generated using k nearest neighbors. So I take a random point here, then k nearest neighbors. If you use k nearest regressor, for example, you'll sum up these three and give you the average. It'll go always
No, in this case, if you use k-nearest, all our stars will not circles.
No, all are stars, but what it'll do is, it's k nearest regressor. So it's going to take the blood pressure of all three, find out the average, give the average to this new point.
So that can be circular.
That can be?
That can, so there are two classes, star and circle. So if you don't,
It works only on the underrepresented class. It generates synthetic data only for the lower class. So in this case, it will generate synthetic data only for the diabetic class.
So in this case, like if you take this sample and if you decided to upsample our data, at what point we should stop? Like these many samples would be enough. We should not go further beyond.
It will bring both the samples to 100 same level.
So 50-50 you mean to say?
50. It will bring you to 50.
Can you give us some pointers?
Imlearn. Go and search for Imlearn on Google. You'll find that package Imlearn. You'll see a lot of reading materials there. But we will cover in detail in FMT.
Okay. So when you do downsampling, it will reduce the records of
Non-diabetic. It'll really go.
So either we can go with that approach or
Don't do your manual approach of deleting the data. Don't do that. That will be the worst thing to do. Anyway, coming back to this. So what the next thing which you're going to try is, since all data is numeric, let's convert all this data into what is called standard scale, xi minus x bar by standard deviation, right? And that's what I'm doing here. From pre-processing library, I'm calling the scalar function. So it converts every record, every column of this data frame into scaled data. Same way test record is also converted into scaled. On that, I rebuild my model and relook at my scores. As I said, sometimes we expect miracles to happen, it never happens.
Which type of scaling does it use? Which type of scaling does it use?
This is z-scores, central value. Yesterday I told you, scaling does not impact linear models. So you won't see any impact. There's nothing else we can do. It converts into z-scores, xi minus x bar by standard deviation for every column. Centralize the data to 0.
So we have a few ways. One is either we do sampling or downsampling. But right now we don't know which is okay.
Correct.
So we need to try with both and see.
Exactly.
But will that really affect if we do an
100%. It will affect the accuracy of the recall for the diabetic class. 100%.
No, I mean doing it upsampling or downsampling. I think we need to go for either choice. Or compulsorily we have to go for both the choice and then.
That depends on how your data is distributed. It depends on that.
like both and see whichever will be more accurate.
It depends on that. Okay, it's a very subtle relationship with the data distributions in the various dimensions.
So the only solution is
And the threshold management, changing the thresholds. 50% is the threshold, no? So I can say whenever probability is less than 30%, it belongs to red class. Above 30%, it belongs to blue class. I can change the threshold. Right now, by default, it's 50%. If probability of belonging to red class is less than 50%, that means he belongs to blue class. Right now, it's that. So that 50% can be changed to 30% by building wrappers around this model. The number of records is what you have in your data. Threshold is in your sigmoid curves, okay? Sigmoid or any probability-based algorithm. This is my probability dimension, 0 to 1, 0.5. Whenever a function, this sigmoid function says the probability is greater than 0.5, 0.55, 0.56, then it will automatically say that this record belongs to the blue. If it is below 0.5, it will say it belongs to the red. So I can bring down this threshold and I can put it over here, 0.3. Anything over 0.3 belongs to blue, anything below 0.3 belongs to red. So by changing the threshold, I can control the misclassification of the diabetic cases. No, it's not a parameter. You have to build a wrapper around your model. There's no automatic way of doing this. So I'll use a function in scikit-learn. It's called binarize. In case you're very impatient and you want to know what it is, please go and explore this function binarize, B-I-N-A-R-I-Z-E. How using binarize we can control the threshold, explore that. If you're not able to find, I'll tell you how to do that in FMT. Which models are suitable for time series? When you talk about time series, automatically only one model comes to the mind, ARIMA, A-R-I-M-A. It's a time series based modeling, which is basically linear regression applied on a time dimension, right? So you'll explore that. You have anything on time series to be done?
No, because I was IIT in the most.
Then you'll have to learn.
My focus on subject study is.
Yeah, ARIMA is linear regression on time dimension.
But that is very on forecasting. Suppose I want to have optimal probing states and what is it?
Optimal what?
Probing.
What is that?
Probing network.
Okay. That is basically to look for intrusions and all these things, kind of things.
So at one point of time I want to do a network.
Or network discoveries. I am not able to put any particular algorithm there. Probably we'll discuss this further and design. You bring it up. We'll take it up. All right. Let's quickly start and summarize what we did. Okay. We started yesterday by discussing about linear model, linear regression. Okay. In linear regression, we the algorithm was used to predict the values. The output is the target is values running numbers. Okay. And for that, we discussed how it is important for you to first analyze your data and check which attributes are strongly related to the target attribute. Select only those. Amongst those attributes, drop the attributes which are redundant, that is, they correlate with each other. Remember this discussion we had yesterday. Same discussion continues today also. But before I come to today's topic, we also discussed yesterday that in linear regression, the algorithm finds out for you a needle in the haystack, the best fit line from infinite number of lines using the gradient descent concept. Okay. So the objective is find the right kind of M and the C which will minimize the sum of squared errors. All algorithms have some objective to achieve. In mathematical terminology, we say that all these algorithms are optimization functions. Optimization means minimize something or maximize something. Okay. By using these optimization functions, it identifies for you the best fit line, and the methodology is called gradient descent. Right? Then the linear regression, today we saw how it is used in classification. This is not the only way. There are various other ways in which linear model can be used for classification. When we come to support vector machines, we'll talk about that also. Support vector classifiers. Using linear model for classification based on probability values, you have a challenge. The challenge is linear models extend to infinity. And it makes no sense to have values beyond 0 and 1. So we convert the linear models into sigmoid surfaces. Okay. The sigmoid surface will come to you again and again many times in many different algorithms, especially those who are going to do neural networks. You'll find that neural network uses by default sigmoid to bring in what we call non-linearity. We'll talk about those things later. So linear model is used for classification in logistic regression, where it is transformed into an S-curve, a sigmoid curve, right? But all the rules of data analysis use only the right attributes. Within those right attributes, there should be no collinearity between them. All those things continues to hold here also. Okay. Now I'm going to introduce you to one more model called Naïve base.
Before we go there, can you just give me a brief distinction between covariance, collinearity, and correlation?
There's no difference. Covariance divided by standard deviation, measured in terms of standard deviation, is called correlation. Okay. So if you have xi minus x bar into yi minus y bar, okay. When you divide this by standard deviation of x and standard deviation of y, we measure it in terms of standard deviation units. This is called correlation. If you don't use this, it's called covariance. And whenever two dimensions have a very strong covariance or correlation, they are called collinears. That is called collinearity. So same thing coming in three different ways. Linearly separable is that distribution, okay, whose data points in the feature space have some kind of a gap between their distributions. So I can represent this gap using a linear model. So when I use a linear model for classification, the model is trying to not represent the data points, but it's trying to represent this gap. I'm trying to model this gap between the two. Such distributions are called linearly separable distributions. They may not be linearly separable on one single dimension. There might be overlap. Even on this dimension, there is an overlap. But put together, they might become linearly separable. Question? Shall we move on? Yeah. So I'll extend this discussion a bit further. Here we see the red ones. Okay, this is the distribution of the triangle. This is the distribution of the circles. Same way, distribution of the circles, distribution of the triangles. Okay. The two distributions are overlapping on individual dimensions, univariate analysis. But when you put them together, the two dimensions together, the two distributions get separated out. They become linearly separable. Yeah. So even if I have weak dimensions in my pair plot, I see very weak dimensions. They're very significantly overlapping, but the central values are slightly away from each other. Maybe a combination of these weak dimensions put together will give me this. But unfortunately, in PIMA diabetes, none of the dimensions give me this.
I didn't understand the point. You told that two dimensions are overlapping each other.
In two dimensions, the classes are overlapping each other. Okay. So in PIMA diabetes, if you see the diagonal, all the classes or central values are significantly overlapping. If you have even a single one, which is central values are shifted away. Okay. Maybe another single one where the central values are shifted away, not significantly shifted. Maybe these two together will be able to give me a linearly separable classes. But unfortunately, PIMA diabetes, all the dimensions, if you observe carefully, the central values are sitting on top of each other. Analysis of variance uses the difference between central values to tell you what is the probability that these two belong to different class. So as long as the central values are overlapping, there's not much you can do. The body of the distribution overlapping is still tolerable, but central values are overlapping. That is the problem. All of you okay? Shall we move on?
But what we analyze is just one. So we didn't analyze two different variables together.
We did no. We saw in diagonal. Look at the scatter plot also. Scatter plot also, they're all sitting on top of each other. They're eclipsing each other. Scatter plot also, the blues and the yellows are eclipsing each other. So the centroid of the blue cluster and centroid of the yellow cluster, they should not be eclipsing each other. All right, let's go on to this new one, Naïve base. This is purely statistical model. It's based on the Bayes theorem, which I presume you people have already covered in the statistics class. Don't say no. Right. Okay, so let's see what is this Bayes theorem, how is it used in modeling. This model, this algorithm is based on the Bayes theorem. It is used for classification. Again, it uses probability values to decide which class a test point belongs to. This is the only algorithm which gets this term associated with it called Naïve. The term Naïve is not a very good thing to be associated with. Okay, but this algorithm is the only one which gets associated with that, very unfortunate, because all algorithms are naive as per this definition. The reason why it's called Naïve is this algorithm assumes that all the variables that you're going to use to build the models, those variables are independent of one another. The independence assumption is often violated. We already discussed this. But then this is true for all the algorithms. It's called Naïve due to the assumption that the features in the data set are mutually independent. They don't interact with each other. But that's what every algorithm does. So this is the only one which gets the cap, the hat, whatever you call it. But the beauty of this algorithm is, what this algorithm says is, howsoever weak predictors your features may be, don't drop them. Consider them. Take into account the information given by each feature and build your model based on probabilities. So it doesn't advocate you from dropping any of the features. Howsoever significant the overlap might be, use them. That's what this algorithm says. To understand this algorithm, we have to understand what is probability, we have to understand what is joint probability, and we have to understand what is conditional probability, 3 of them. So let's quickly start. What is a probability? How do you define probabilities? Okay, chances of some event occurring. So in the definition, you have an event, and then you have something called chances. What is chances? How do you find that out? How do you find the chances of something happening? So what involves the experiment? What is there in the experiment? Trials and proportion, right? So if I ask you, what is the probability that today it will rain? And you might be surprised, just a week or 10 days ago, there was news in the web where in Kerala there was snowfall. Have you seen that? In Kerala there's a hill spot, Munnar, right? There they had snowfall and the temperature was -3, right? So such events can happen. So if I ask you, what is the probability that today it's going to rain at 5 o'clock? Why did you say 0? Who said 0? Yeah, why 0?
Sunny.
So
I don't see any clouds.
So
Check my weather.
don't check the weather. Just talk. So what you've done is you have taken your past experience into account. On this particular date, month of January, almost middle of January, how many times in the past did I see rain? That ratio, how many times you saw this event of interest versus your past records, the number of trials. This ratio is called frequentist approach to probability. So the probability is a ratio where it's a ratio of the events of interest to you, how many times they have occurred, out of the total number of trials, how many times the event could have occurred. That is a ratio called probability values. Did you know that probability values can be calculated in another way? Have you done Poisson distribution in statistics? Poisson distribution, very convoluted formula there. If given the state I am in, what is the probability that I'll be in a different state, the next state? That is a function of how many ways you can reach that state. Okay, so that is another way of finding probability. We are going to use the previous definition of probability, which is based on frequencies, ratios. Okay. Now that you know what is probability, the next thing you need to know is what is joint probability. Joint probability is probability of multiple events occurring together. Okay. So what is the probability of, if I give you a deck of cards and ask you to pull a card out of it, and I ask you, what is the probability that this card is going to be a red king?
1 by 52.
1 by 52 is red.
No, you never played cards.
2 by 2
You have 52 cards. Red king.
2 by 52.
Red king is 2 by 52. So there are 2 colors, red and black, 52 cards. So 52 cards, you have 2 red kings, hearts and diamonds. So the probability of this joint event of red king is, red is 1, king is 1, the probability is 2 by 52. Alright? Now when you're pulling out the card, somehow you come to know that it is a red card. Somehow you come to know it's a red card. Now what is the probability this is a red king? Now you know it's a red card. So your scope is now limited to only red cards, 2 by 26. 2 by 26 is 1 by 13. So you have taken into account an evidence and information that you captured that it is a red card. The moment you get that information, you recalibrate your probability of red king. That concept of recalibrating your probabilities based on the information that you're gathering, that concept is called Bayes' theorem. So what Mr. Bayesian said is, start with some probability, the default probability values, but keep on recalibrating those probabilities the moment more and more information comes to you. Howsoever the information may be, howsoever weak the information may be, don't ignore any information and recalibrate your probabilities. That is the philosophy or reasoning behind this Bayesian theorem, Bayesian models. Are you all okay? So for this, to understand this, we need to know probability, joint probability, and your what is conditional probabilities. Conditional probabilities, what is the probability of king given it's red? We know it's already red card. So now only the event left to happen is king. So what is the probability that this card will be a king given it's red? That concept, which you call 2 by 26, that concept is called conditional probability. So we started by joint probability. What is the probability it's a red king? Because we didn't have any information. It was 2 by 52. The moment we came to know it's a red, then we switched to conditional probability. What is the probability is king given it's red? Right? Conditional probability is invalid if joint probability is 0. If probability of two events occurring together is 0, we don't talk about conditional probability. What is the probability of drawing a green king? There is no green king possibility. So don't even talk about conditional probabilities. So we talk about conditional probability only when we have joint probability greater than 0. All right? So let's see how all this was put into build a model. We already discussed this. What is probability? What is joint probability and what is conditional probability? We already discussed this. So I'm going to jump these slides. This is the model. I'm sure you would have seen this formula. Looks very familiar. Wow, man! You should put it on some kind of board and put it on. Looks so like you're going to launch some rocket. It's all very easy. Okay, so what I'm going to do is I'm going to jump all this slides back. I'm going to explain with some animations. This blue box represents all the flight information I have captured from my experience. All the 100% flights which I have taken, I'm representing it by blue box. The dimensions of the box are inconsequential. They don't matter. When I look at my past data about the flights which I have taken, I notice that 20% of the time there was flight delay. 80% of the time the flight was on schedule. In mathematics in school, you would have done this as Venn diagrams. Okay. I also noticed from my past information, past data, that 5% of the time there was fog at the airport. Now it's natural for us to quickly link fog with the flight delay. Don't do that. We are not here to say that the flight delay was because of fog or fog was because of flight delay. We are not here to establish that link. Naïve's algorithm assumes that these two events are independent of each other. Whatever the reality may be, the algorithm assumes these two events are independent. They have nothing to do with each other. Okay, but we know through our experience that they are not really independent. But the algorithm assumes they are independent. Okay, and we know that if I mark this as flight delay, no fog, this is fog but no flight delay, this crescent. This is the case where flight delay and fog occurred together. That does not mean flight delay led to fog or fog led to flight delay. We don't know. We are assuming that they are independent. What's going to happen is, the lesser the overlap, more unlikely they are linked. The more the overlap, more likely the two events are linked. They influence each other. But I repeat, we are not here to establish any causal relationships. We are assuming that the two are independent.
So you mean to say, suppose there is a strong relationship from our intuition that for a particular use case, we found that there could be a strong relation. There we should not use naive Bayes in that case.
Correct. We should not use naive Bayes. All algorithms are like that. All algorithms show you the independent variables orthogonal to each other. That means they are independent of each other. Mathematically, when two things are independent of each other, they're shown at 90 degrees. If two attributes are very strongly influencing each other, you have to replace them with one synthetic dimension, PCA, or drop one. You have to do that. Same thing applies here also. Shall we move on? Okay, now look at this. Let's look at this region closely. This region is the intersection region, okay? Probability of flight delay and fog, the two events, the joint probability, okay? Now I told you I want conditional probability. Now that I'm seeing fog at the airport, now that the card is a red card, what is the probability there'll be flight delay? Now that it's a red card, what is the probability it's a king? So what happened? Your base, which was earlier 52, it shrank to 26. Same way here. Now that I'm seeing fog at the airport, what is the probability the flight will get delayed? So the base becomes fog. And the numerator is this area. So probability of flight delay given fog, the conditional probability is this intersection area divided by the blue. So if this is red cards, this is red king, these are the other cards. So what is the probability of red king? It was 2 by 52. But now that I know it's a red card, that means this is not my base, this is my base. What is the probability it's a king? Numerator by denominator. All right, all of you okay? Okay. Let's move further. I'm going to write this equation on one side and play around with this equation a bit. Caution, be ready to slip. So P A condition B, this I'm showing it here as P A intersection P by PB. A intersection B by PB. All of you okay? Can I rewrite this equation and rewrite this equation 1 as PA condition B into PB is equal to PA intersection B? Can I do this? Can I do this? All of you okay? Okay. Look at this PA intersection B. Does it make any difference whether I write this as P intersection B or PB intersection A? Does it make any difference? Okay. If P intersection B is this, then PB intersection A, where the numerator is changed and the denominator is changed, it becomes PB given A into PA. Okay, I take this expression and I put it over here. So this conditional probability becomes P intersection B is PB given A into PA divided by PB. This is your Bayesian model. I'll tell you what it means. This is all algebra. But let's understand what it means. What is the probability of a person being diabetic given the conditions? So this is the class diabetic, non-diabetic. These are the independent variables, the BP, the plasma, and all these things. So what is the probability a person is diabetic given the conditions? What Mr. Bayesian said is, instead of building models, go back to your data. From your data, pull out all those records where people were diabetic. How many of them had these conditions? This is called likelihood ratio. Go back to your data, from the data pull out all the diabetic cases, how many of them had this condition? So in some building models do this, likelihood ratio. Multiply that with what is the probability of anybody in the population having diabetes. So this is my base probability. What is the probability is reigned today? 0% based on past experience, and this is that probability. Recalibrate this using this likelihood ratio. What is the probability of red king? 2 by 52. We modified that into 1 by 13. That is recalibration. That is what this numerator is doing. So this is called likelihood ratio. Prior knowledge, you already have knowledge about this ratio in the universe. And this is called evidence. I'm seeing this occurring. Given that it's a red, I'm seeing that occurring. This is evidence. So the argument which Mr. Bayes put is very simple. He did this 200 years ago. He said that instead of trying to build a model for this, go back into data, pull out all the cases which satisfy the condition, which are diabetic, belonging to that class. How many of them had this conditions which you're seeing today? That's all to this model. So this model, this is called likelihood. This is called prior. This is called evidence. And whatever you come out with, this is called posterior. And we do this in common sense. I'll give an experiment to you. Are you all ready? Yes. We actually use Naïve in our day-to-day life. Lakshmi, is it going to be male or female?
Lakshmi Kant is
Lakshmi is evidence now. Is going to be male or female? So what you're doing is you're going back to the past. How many times you have come across this name where it was a female versus where it was a male? So you're pulling out all the past Lakshmis that you have in your mind. How many of them were males, females? In how many of that's Bayesian probability. I have a friend called Lakshmi Narayan Babu. And this one particular name I'll not forget because there was one class which I was supposed to attend and the class was being taken by Lakshmi. Every door I opened, there is a male standing there. Every door I opened, there was a male standing there. So it took me some time to understand that this guy's name was Lakshmi. So I did a wrong interpretation. Lakshmi means female, but there are people, males with name of Lakshmi. Right? So what you've done to answer this question is Bayesian probability. Right? So it all looks strange, but we all use it day-to-day life. Shall we move on? Okay. Any questions on this? Yeah, this one will give you that. That reminds me. Okay. So before I move on, when you read about these algorithms in books and articles, you need to be slightly careful. So let me explain what the problem is. So what happens is, what is the probability of A given B is equal to probability of B given A into PA by PB. All right. Many of the authors, okay, what is the probability of not A given B? So whatever this probability is, 1 minus PA given B. Okay. So this I can write it as, all of you understand what I'm doing? Probability of A given B, probability of king given red. What is the probability of not king given red? That's what we're doing here. So this I can write it as P B given A into PA by PB, which can be further written as PB by PB. Agreed? All of you okay? So whether you're finding probability of A given B or not A, I'll put it as like this, not A given B, both of them have in the denominator PB. So it is not PB which is going to decide whether this is going to be class A or class B. What is going to decide whether it's going to be class A or class B is the numerator. The numerator. If this crosses 0.5, he's going to belong to class A. If this crosses 0.5, he's going to belong to not class A. Get my point? So what decides your class is the numerator, not the denominator. Denominator is same in both. So many of the authors, they don't reflect this. They say that this is the Bayesian model. And you will keep wondering, where did the PB go? So the reason why they don't show PB is that it's the numerator which decides the class. However, in case you want not the classes but the probability values, then you'll have to divide the PB. All right? And the reason why they don't show PB, they often say that PB is a constant. What the hell? What do you mean by PB is a constant? PB is a constant. Some people say that since this is an evidence has already occurred, this is 1. Probability of an event which has already occurred is 1. So they use that argument also. But the argument is, mathematically, for classification, PB is not important, so it's not shown. All of you okay? Okay.
In this diabetes statement, so the PB of A is doesn't go in diabetes, what?
Given the evidence, given what you see.
And E is already.
Sorry.
What is P in this diabetes?
This is, anyway, how many people in the population are diabetic? Yeah. No, diabetic. Which symptoms we don't know. In the population, how many are diabetic? What percentage? That is this PA. How many are diabetic with these symptoms? Likelihood ratios. Okay. Now I'll go back to the slides which I jumped, or should I go forward? Just 1 second, let me check. Yeah, I'll go forward and then go backward. So I have a data set. This data set is 100 records. You see 100 in the bottom right. Total number of records is 100. Of this 100 records, 80 records no flight delay, 20 records flight delay. That's what I showed you in the Venn diagram. Okay. 20 times when there was flight delay, I noticed 4 times there was fog at the airport, 16 times no fog at the airport. This is that overlap between fog and flight. I also noticed that 80 times when there was no flight delay, 79 times there was no fog, 1 time there was fog. This is the same Venn diagram which you saw earlier. Okay, if you're getting confused, this area is no flight delay, no fog. This area is fog, no flight delay. This is 1 time which is occurring in my case. Yeah, the blue left out region is no flight delay and fog. This crescent which you see here is this one. No flight delay and fog is this. This is the crescent. Okay, we convert this into ratios. 4 by 20, 16 by 20, 1 by 80, 79 by 80, we convert into ratios, the likelihood ratios. Now once you convert into ratios, you can use any permutation combination to find the probability. This is what we have seen earlier. Okay, you can put those ratios over here and you see the calculations. Okay, what I want to show you is I can extend this argument. To include multiple parameters. Once again, I have only 100 records. 80 times no flight delay, 20 times flight delay. Okay, and these are the various events which I have captured from the past. These are my attributes. So 20 times when there was flight delay, 4 times there was fog at the airport, 10 times there was technical snag. Oh, what is this? Oh, this, okay. Yeah, 0 times there was pilot fatigue. Okay, so these are all my observations which I convert into likelihood ratios. Keep in mind, these don't have to total up to 20. They can be overlapping regions in the Venn diagrams. They don't have to total up to 20. What I mean is, in the Venn diagrams, these regions might be overlapping each other. Okay. So I convert everything into likelihood ratios. Now look at this. Probability that flight will be delayed, given that I am observing fog at the airport, but no technical snag reported. How do you find the probability that when I see these two events occurring? Use the formula, treat the event of flight delay as A and the combined event as B. So it's again probability of A given B. Okay, PA given B is nothing but probability of flight delay given these two conditions. You know how to handle this? It becomes PB given A into PA. You're going back into your records and seeing how many times flight delay happened, how many times these two events occurred together in that records. That is what this expression is.
So the likelihood is B given A, right?
Likelihood ratio.
Table.
Correct. Likelihood ratio. So PB given A, B is a compound event right now. So P given A is this. PA continues to be PA. That's nice. Who did that? Okay. Divided by probability of B. PB. So you can form any permutation combination of these events and substitute into this equation over here, the likelihood ratios, and I'll tell you the probability. What is the probability of flight delay now that you're observing these events? So you can keep on recalibrating your probabilities. Forget flight delay. What is the probability of an intrusion, network intrusion, given that I'm seeing this IP, I'm seeing this login ID from this particular geographical location? So you keep on recalibrating your probability values. The moment you see such events in the log files, the moment the probability value crosses a threshold, you send your alarm. Right? But there is a problem. We have time, so we'll discuss the problem. What is the probability of flight delay given fog at the airport and say buffaloes grazing on the runway? I don't have any data about buffaloes grazing on the runway. So this algorithm will give you the probability is 0. Okay, this comes from experience. Earlier in Delhi, we used to have Palam Airport. Palam Airport had no boundary. So you can see a lot of buffaloes coming from the villages and grazing sitting on the runway, right? So what is the probability of flight delay given fog and buffalo at the runway? The algorithm will give you 0 because you don't have any such information with you. So for that, we use something called Laplace smoothing factor. So Laplace smoothing factor sounds very hi-fi, but it's actually adding one small to the numerator, adding one small 0.0005, a very small number. You're free to add any number you like. This very small number prevents the numerator from becoming 0. When those rare events occur, for which you don't have data. Okay? Since the event is very rare, we give it a very low value. There's a lot of technical discussions behind this, but this is called Laplace smoothing factor. By default, it's a very small value of 0.00005. Any outlier, any event comes in the test record, which you have never seen before. So at that time, the probability should not become 0. So probability very low value. That low value comes because numerator is very low. So any rare event for which you don't have any training data, when it occurs, this expression will become 0. But this will prevent it from the numerator from becoming 0. So the probability value will be conditional probability will be very low. Generally, it's a prefixed constant, but you can change it if you like. Any other question on this? Shall I go back to the slides which we jumped? Now those slides which earlier looked like hieroglyphics now will make sense to you. So this is where we jumped. Is it okay? So posterior probability is this, which you're trying to find out. Prior, not prior, this is my likelihood ratios. It's also called conditional probability. I mean, this can also be called conditional probability, but this is posterior, this is likelihood, this is prior, this is my evidence. Some books, some authors will reflect it like this, but it means the same thing. So the class that will assign to a test record will be whether this numerator is greater or this numerator is greater than 0.5. That is called argmax. Okay, so whichever numerator is higher, accordingly the class will be assigned to the test label. So that is indicated by this. The technical name that we use for comparing the numerators are argmax. Which one is maximum, higher?
You mean whether PB is greater or PA is greater? That's what you mean?
Now, whether this numerator, and there was one more numerator here, right?
1 minus.
Oh, okay.
So let me rewrite the numerator here. So this is PB minus PE given B.
No, B given.
Correct. It's opposite.
1 minus, no. So this will be 1 minus PA given B is this, given A into PA by PB. So what this will become PB, and this whole thing will become PB. So now argmax compares this with this, whichever is greater than 0.5, that class will be assigned to the test label. Then important thing, too much of words, but let me tell you in a brief way, because this algorithm assumes all these different events to be independent of each other, they don't influence each other. In probability theory, you would have seen when events are independent of each other, we multiply their probabilities. See, I told you. So when events are independent of each other, we multiply those events. Remember that in probability theory? So in the base, since the events are independent of each other, we multiply these events. What I mean by this is, look at this example. Look at this example. This is my numerator, this is my denominator. Probability of fog, no technical snag. Probability of fog, no pilot fatigue, no passenger delay. If you want to find all those things out, just take individual probabilities and multiply each other out. Right? I'm not showing multiple things over here, but you can just multiply the individual probabilities over here to find the PB. B is the condition. So in diabetic case, it was this represents blood pressure, it represents plasma, it represents something else. So I can say numerator, where I'm using it, what is the probability of your diabetes given blood pressure? What is the probability of diabetes given plasma into what is the probability of diabetes given this, that? So just multiply those events because they are independent events. That is what the numerator will become, right? Same thing is shown. You will come across this expression. Don't get scared with this. This is what it means.
The same equation we will repeat for each of the.
Yeah, each of the attributes. Multiply.
Class.
Yeah, W is a class. Which class it belongs to? All right. There is actually a lot of depth and discussions on this, Bayesian probabilities, which I'm assuming you're done in statistics. I'm going to move to the hands-on. Before I go into hands-on, advantages, disadvantages. Just like your logistic, it's very fast both in training and testing. K nearest neighbor is very fast in training but very slow in testing, because it has to find so many distances to find the K nearest neighbors. Does well with noisy data is what you will see in many of these books and articles, but noisy data means there is a lot of jiggle in the universe from where you are taking the snapshots, which means 2 consecutive snapshots will have different distributions. Okay, so you have to take this with a pinch of salt. Any algorithm will find it difficult with noisy data sets. Requires few examples for training. Again, something which we need to actually take with a pinch of salt. As long as the few examples are good representation of the universe, but otherwise no. We can convert our class into probabilities. Sometimes probability is useful. Predict underscore proba. So we make use of the probability, predict underscore proba, the probability values, to actually change the thresholds using binarized functions. Okay, we'll talk about that later. Biggest disadvantage is the assumption it makes, but then that is the assumption made by all the algorithms. When you have too many numerical variables, first it will convert these numerical variables into bins, boxes. Okay, it will categorize them, create bins, and then calculate the probabilities. People have said that the estimated probabilities, conditional probability, is usually less reliable. It's not reliable. That is true because these probabilities, assumption is the attributes are independent of each other. But because attributes are not independent, these probabilities have to be further jacked up. That is the same problem that you saw in p-values. Between MPG and horsepower, if there is a relationship and there's a p-value, why should that p-value change when you use, along with horsepower, the weight of the car also? Both the coefficients and the p-values for the horsepower change when you add some more dimensions to your analysis. That happens because of the collinearity between horsepower and the weight column. So this is true for all the cases. Estimated probabilities are, so estimated coefficients are usually different from the coefficients in practice. If you come across a rare event, then the numerator can become 0, but we can handle this using that Laplace factor.
So one more regarding disadvantage. See, you are considering all the attributes. Say you have huge number of attributes. So will it be slightly slower these days because you are considering?
It will be relatively slower to less number of attributes. Yes, it will be, but it will not be visible to you. It will not be significantly different. However, you need to be aware of curse of dimensionality. You should be aware of curse of too many dimensions, too less records. Then this any algorithm can end up in curse of dimensionality. Shall we try this on the Pima indents dataset? Okay. Okay. Before I proceed, in the UCI dataset, have you seen the UCI repository? To my knowledge, there are 512 datasets. Pretty rich source of data. I might cover in the class Pima diabetes datasets, but nothing prevents you from going and building these models on the bankdata.csv, where you to predict defaulters versus non-defaulters. Just go ahead and practice this. Don't worry about the accuracy and all. How do you tweak the accuracy to a further higher up level? That will deal in feature engineering model tuning. But first thing that you should do is get used to the libraries that you need to call. Second thing you need to learn is the basic syntax of scikit-learn. Third thing, by the time you become comfortable with all these things, then we can go into model tuning. Okay, so that will bring in continuity in your, I know many of you are on jobs, you'll find it difficult for the continuity to be there. This is one way of ensuring continuity. Yes, sir.
Why is it not suitable
It's a ratio, so the ratios will have to be, first it will have to bind. Do you know that even decision tree does that? When you use it for classification, it has to bind. So if I have an attribute called plasma, it will bind first, equidistant bins will be created. So if you have too many numerical variables, it will take time to do that. But however, we will not see all these things because we have today modern computers which are very fast, powerful. This algorithm was 200 years ago.
Problem was with slowness, not with the accuracy or.
No.
So it was only with the performance.
Performance.
So decision tree also making the condition.
They are all under the hood. They are all related. Decision tree also creates based on entropy and Gini index, the homogeneity. That is another way of maximizing Bayesian properties.
So the question was different. What we are testing this condition decision tree.
Yeah.
Those also make use of conditional probability.
They are conditional probabilities. Absolutely. What is the probability of class A given income is this, age is this, and this is that? That is what the path is. Yeah, they are using a different loss function. So all algorithms do the same thing in different ways. If you understand this, you will not have problem in learning any algorithms. So decision tree is all the conditional probability. The path is the condition. Based on the condition, what is the probability of finding this class?
I don't know whether it's legit or not. Can we do like that? Let's say 0, 1, 0, 1 we have. Can we predict whether the next value will be 0 or the next value will be 1?
What do you mean by that?
And this is a sequence, like regression follows the sequence. What is the pattern of the data?
Yeah.
In that way, it says, let's say the next value will be, there might be a possibility that the next value will be something. Whatever. Can we do in that way? Like let's say we see 1, 0, 0, 1, 0, 0, 1. Okay, this is the pattern going on in some data, and we will run a prediction model. Can we predict the next value?
Predict what's the next value going to be.
Seeing the pattern of the whole. Like in 10th or 12th exam, we see 2, 8, 9. There is a pattern inside. Let's say. Can we do it that way?
Only if you see a pattern, you can build models. If you don't see any patterns, you can't build models. He brings me back to one more very core issue, very core point that you need to be aware of. We build models only when, this process P, it takes as input something and output, okay? This output that it generates, this output should be, usually it's, say if it's a numerical value, it should have some kind of a distribution. The distribution will have a central value and some spread and so on and so forth, the characteristics of distribution. Okay. Only when you have well-behaved, well-defined processes like this, whose outputs have some well-defined shape in terms of the central values and the spread, only then we can build models to represent this process. If the output of this process is going to be random in nature, we don't know what it's going to be. Sometimes it's 10, sometimes it's 40, sometimes 9, random outputs. We cannot build a model to represent this. You can build models only for those processes which are well-defined processes. So coming to your requirement, if the output, the 1, 0, 0, 1, 0, whatever you're seeing, it's an output of some process. If the process is outputting this in some patterns, the pattern could be in form of Gaussian distribution, so on and so forth, only then you can build a model to represent that process and predict what's next value going to be with some confidence levels. You can't model a random process. If that 1, 0, 0, 1 and all is coming out randomly, then you can't build any model. Yes?
I understand what is the PA with condition B, right? The standard formula is one. So now we are actually calculating PAB by putting PBA condition. So yeah, we are getting an output, but what is the need of doing that? Is it that previous numerator values is not calculable or?
No, you are depending on past data. What is the probability of now a patient walking into my dispensary? I want to classify him as, does he have benign or malignant, cancerous or non-cancerous? Instead of building a model which is where input is the attributes of the patient and building a model to predict that, go back into your data set of the past patients, those who were cancerous, how many of them had these conditions? If majority of them had these conditions, then likely this guy is going to be cancerous. If the past data shows that amongst cancerous patient, this kind of attributes was very low, then maybe he will not be a cancer. So I flip the argument and go back to my past data and see what is the likelihood ratio given the past.
We can do same thing in this prima case because here also what we are saying is.
That's what you're going to do. Correct. That's what you're doing here. That's what you're doing. So shall I get in the hands-on? Okay. It's the same data set. So all of you know what the problem is. Okay. We have the wine data sets, this thing, but we can do this on. Okay, would you like to take this as homework? Apply this Naïve algorithm on PIMA data sets and see what is the result. You have to give me overall accuracy and class level accuracy. Right? All of you okay? Would you like to give it a shot? Okay. Then let's go through this wine data set. Naïve wine. Okay, this data set has come from Italian wine brewery, wine farm. Okay, this is a real data set. Apparently, there are 3 different.
Wine data set, we don't have it. We don't have wine data set, that wine.cs.
You don't have data set? Okay. Don't worry, I'll pass it on to you. It's there on the pen drive, she'll pass it on to you. This is wine.csv, not red.
Some people it's red, some people it's not.
But you can try it on red also, it doesn't matter. They're the same, this thing. Source is the same. All right, now the requirement is there are apparently 3 different classes of wine makers. Okay, and the situation is the way the wines are classified. I wonder if you people know how it's classified. You have specialized, skilled people who actually taste the wine and they give the classification, the quality of the wine. Yeah. So this is one of the most unenviable jobs, or rather enviable jobs, where you get paid for drinking on the job, right? So the requirement is, can you build using data science a model which takes as input the various parameters of the wine and it tells you what the class of the wine is going to be. So I can replace these people with automated systems. That is the objective, okay? So if you look at the data set, these are the columns available in the data, which I have noted from that UCI data set. The cultivator, alcohol levels, malic acid, ash, alkalinity. Honestly, I have no idea about these things, but these are the various parameters available. So when I load this data set and do a df describe once again is used to identify the tails. Look at any of these columns. We'll just look at one. Take your, okay, look at this, interesting. Look at the cultivator is a categorical variable, so don't look at that. Look at alcohol, mean is 13, median is 13. Malic acid, mean is 2.3, it's almost 2. Ash 2.3, 2.3. Alkalinity 19.49, 19.5, almost same. So every attribute, the mean and median are almost coinciding. So there is that, to that extent we are safe. Look at the tails. This tail is, sorry, start with this. This is almost 1 unit. Yeah, it's 1 unit, and the left hand side tail is also 1 unit. This is 2 units. This is almost 2 units. This is 2.5 to 3.5 units. This is 1.3 to 2.2, almost 5 plus units, 0.7 units. Every dimension, mean and median are coinciding, and the tails on the both sides are almost equal size. So looks like most of the dimensions, there is not much long tails or skews. Only one dimension you will see, which is magnesium. Mean is 99, this is 98, a difference of only 1 unit. Central value is no problem. Look at the tails. 10 units. Sorry, this is 18 units. 18 units versus 55, 54 units. Yeah, this tail is very long compared to the left hand side tail. So this is when your central values are overlapping, 98 versus your 99, central values are overlapping, very small shift. That means you have only a few outliers, very few outliers on the right side. Otherwise, the mean would have been drastically pulled to the right side. So 1 or 2 records seem to have outliers on that one particular dimension.
So should we go ahead and do it?
All outliers have to be handled.
And then means like
Replace them with some different values. Dropping records is the last option. You may have to, but it's last option. The visual way of seeing this is pair panel, and this is the pair panel. I'll come back to this code. I'm looking at the data types here, but I'll come back to the code. Look at the distributions, and I want you to compare this distribution with PIMA distribution. So let's compare this with PIMA, okay? There are 3 classes and hence 3 curves. And look at these curves. They are overlapping. They are overlapping, but you see the difference? What is the difference? Central values are separated apart. The means are not overlapping. And that makes a huge difference in your ability to distinguish the classes. In PIMA, the problem was even the central values are sitting on each other. So the body is significantly overlapping, but central values are separate. So we are in a better condition than we were in PIMA. Look at this column. The blue and the orange are overlapping, even the central values are overlapping. But at least the green is away. So all the columns, this is, I think this is the worst column we have. This is in your data sets, where all the 3 columns are absolutely sitting on top of each other. This one. And this is ash. Okay. Ash, all the columns, all the classes are sitting on top of each other, including the central values. However, because I have other attributes which can help me segregate, I can ignore this. Right? There you go. So in many of the dimensions, 2 classes are overlapping, but as long as the third one is away. So this is what I was saying. If you have a dimension in which the 2 classes are significantly overlapping, small change in shift, but when I combine this with another dimension, the 2 Gaussians, they become linearly separable. So I'm seeing this distribution this way. I'm seeing this kind of overlap. I'll redo this. I'm seeing this kind of overlap. When I use another dimension, in the other dimension also I'm seeing an overlap. But when I put them together, in that mathematical space, the 2 Gaussians become linearly separable. Because of that, linear separability now possible amongst the classes on the dimensions. Look at this dimension. This one, I don't know which one is this. This one is not going to help you separate the orange from the blue. Doesn't matter as long as I have this dimension with me, which separates orange from the blues. So one dimension will compensate for the other dimension. So overall, these weak predictors put together become strong predictors. Exactly. Overall, these weak predictors put together become strong predictors, and as you will notice when you go down the line, let's look at the data types. We don't have any non-numerical columns here. Everything is numerical. Keep in mind, all algorithms need numerical columns only. Numerical columns could be categorical or real numbers. Come down. So I'm separating out the X variables, independent variables. The target is the cultivator. I'm splitting my data into training set, test set. I'm splitting my data into training set, test set. Yeah, are all of you with me on this? Okay. You can actually download the data set from UCI if you wish to. This data set you can download from UCI and run the code. Very good. I'm instantiating the Gaussian Naïve here. There are different variants of Naïve. This Naïve assumes that the dimensions are Gaussian on each one of these, the distributions are Gaussian on each one of the dimension, and we meet that requirement very well. On all the dimensions, the classes are distributed in almost Gaussian ways. Gaussian means looks like normal distribution. So a perfect case for Gaussian Naïve. So I'm calling Gaussian Naïve here. There are other variants like multinomial Naïve and other Naïve which you can make use of. So I'm instantiating the model here. I'm going to do the model fit here. This is where our Naïve likelihood ratios will be calculated. And then I look at this. On the training set itself, I'm doing a testing. It's giving me 97% accuracy. Why am I doing this? I'll tell you in a minute. While I can also do this model on the test data. Here I'm running the model on the test data. Okay. And in metrics, there is a function called classification report, which gives me this, all these metrics, recall, precision, everything in one shot. If you're interested, you can separately print the matrix also, confusion matrix. Now look at this confusion matrix. Look at this. Look at the class level recall. Look at the class level recall. Any problems? Hey, Molly, any problems? From SQL and import Gaussian. Okay. All right. Now look at this. There are three classes here, 1 to 3. And look at the class level recall. What is class level recall? Accuracy at class levels. Almost 100%. 1 means 100. 95%, 100%. So each one of the classes, it's able to accurately classify with a degree of, this is what we wanted in PIMA diabetes. It's giving us accuracy in wine data set. Okay, I'll talk about this micro average and all these things down the line. We'll talk about this later. Right now, just look at this recall matrix. I've not told you what precision is. And look at the confusion matrix. Actual number of class A in your test record is 23. All of them have been classified as class A. Actual number of records for class B in your test data is 19. It has correctly classified 18. 12, it has correctly classified 12. You are able to achieve this kind of a score in this model, even though the dimensions are overlapping, the classes are overlapping on all the dimensions, because of some dimensions which come together to make strong predictors. So you should understand the difference between PIMA diabetes and this. In both the cases, the classes are overlapping, but there's one very important critical difference. And it's that difference which is making this, right? So you can run the same algorithm, Naïve, on PIMA diabetes and see what is the score you get there. Your job here is to select the right attributes.
But here we are not giving the all in.
That this is, you will never get data on a plate when you're doing real life projects. This is only classroom. But when you do sit down and do real life projects, your customer says, suppose a simple example, can you use data science to improve my customer CSAT rating from the current 3.5 to 4.5 out of 5? Can you do something using data science to help me improve my customer rating in my technical support? These are the kind of requirements which will come to you. Data will never come to you. So now your job is CSAT rating, customer rating for technical support. What kind of data you need? Not decide. You have to first guess what kind of data I need. Your domain expertise will help you. If you don't have it, you'll need to have domain experts. So for CSAT rating in customer tech support, what kind of data I'll need? Can somebody go back to the past tickets? Okay, go back to the past ticket. What kind of data you need? Go back to the past tickets. From the past tickets, you collect what kind of ticket, P1, P2, P3 tickets. I need to find ticket classes. Then whether the ticket belong to hardware, software, or something else, I need those things. And various other, you'll decide what kind of data you need. The next challenge will be, where will you get the data from? Some data will be available within the organization. Some data will be available outside the organization. Some data will be available with the customer. So getting these stakeholders to give the data to us will be such a challenge. So all your soft skills will come into play. Right? So once the data comes in, you have to first establish the reliability of the data. What if the tech support department has given you data where customer is very happy? They have not shared with you the dirty data. Your model will go for a toss. Those are the challenges which you will face as a data scientist. Once the data comes to you on those various attributes that you have, you will do this analysis using pair plot and other techniques. Is this column good or that column good? Which column should I use to define customer satisfaction? I come from the IT world just like you do, many of you do. We people have done a lot of projects in Java and C and all these things. The project starts with customer requirements, which we turn into technical requirements, that we turn into design requirements, that turns into code specs, coding requirements. That turns into unit testing, integration testing, and finally, then we go for acceptance testing. In acceptance testing, usually it bombs. Right? The reason why it bombs is we look at data only in the last stage. Then we come to acceptance testing. We ask customers to give us some data. In data science projects, your project will start with data, the project will end with data. Data is the core. You will be revolving around the data sets. So 80% of your effort, estimated effort in data science project, you will see that when you do the capstone project, we'll go and getting the data itself.
So it's usually start with data-driven approach and end with
100%.
And end with data-telling stories.
Yes, 100%. Visualization and storytelling from the data. That is what data science is.
So in between that data analysis.
In between the data analysis, feature engineering, feature selections, model tuning, all these things come in between. So please don't make this assumption. In this hands-on exercise we are doing in the class, you're getting all the data from, right? This will not happen in real world. That's why when people come and do capstone projects, many of them want to do self-driving cars. So we have to take them out separately and tell them, hold on. At least a decade of research has gone into building those self-driving cars. You can't do it in 4 months. So when you come to capstone project stage, you're very far away from that. Please sell it to capstone projects with care. Right, guys? Okay. What I'm going to show you is one more thing. Okay. Though this is kind of doing very too early in this for you, but still let me do it. When you build these models, okay, we need to understand how the model is likely to perform in production. Because I'm going to put the model into production, which means I'm going to disrupt many of the processes in production. So the stakeholders in production are going to ask me, what is the performance you expect from this model in production? Suppose somebody asks you this question, what is your answer? Okay, it completely matched with this, what I'm going to cover, because how do you prevent this from happening in production? So when somebody asks you this question, what is the performance you're likely to have in production? We never give point estimates. We never say my model is going to give 78% accuracy or 80%. We always give a range estimate. My model is likely to give me accuracy between 80% to 95%. The moment you give range, that means you're not 100% sure. The moment you're not 100% sure, statistically you're supposed to associate with a confidence level. How confident are you in this range? So usually the confidence level is measured at 95%. So we give a confidence level of 95%. 95% confident that my model is going to give me accuracy between X and Y. But to be able to do those things, find the 95% confidence level for your estimates, we use a technique called bootstrap sampling. In statistics, it is known as sampling with replacements. Okay, and we also use a technique called k-fold cross-validations. So I'm showing you this k-fold cross-validation, what it means, but we'll do this in detail down the line. Look at this. From scikit-learn, import cross-validation score and cross-validation predict. These two functions are available already. Let me explain to you first what is cross-validation. I have this data set with me. Okay, suppose k-fold CV, that which I'm going to use, k stands for an integer number, just like k nearest neighbors, an integer number. Suppose I see k is equal to 10. Usually we take 10 as reliable. What it's going to do is, it's going to break your data into 10 pieces, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's going to break your data into 10 equal pieces. Then what it's going to do is, for I equal to 1 to 10, where I is an index, I equal to 1, 2, 3, 4, 10. For I is equal to 1 to 10, fit using 9, test or predict using the left out. So first time when I is 1, it'll take some 9 data sets, do the fit, and it will test on the left out. Then when I becomes 2, it takes some other 9, maybe this 9, do the fit and do the left out. Then it'll take some other 9, do the fit, left out. It'll do this 10 times because you have taken 10, k is equal to 10. Because you have taken k is equal to 10, it's going to break your data into 10 pieces, train on 9, test on 1. And it'll do this 10 times. Train on different 9s each time, test on a different left out each time. When you do this on this particular data set, so I've imported these two. Cross-val score, I've supplied the model to it, the model which I built up, the training set test label, and CV is 10. When I do this, look at the scores I'm getting. First run, it gave me overall score of 92.8. Second run gave me 92.8. Third run, it gave me 1, 1, 92.3, 92. This is all the scores you have got. Average of all these scores is 96.12. So you can expect your model in production on average to give you 96% accuracy. However, we want to give a range. To get the range, you can find out this distribution, 95% confidence level of this distribution, or resort to bootstrap sample. We'll talk about that later in detail, right? So we make use of this technique to find out overall how the performance is going to be in production. 96% average accuracy score I can expect from this model on this data set.
In this model, when we do model scores, we did train set and train
Yes.
right? We got accuracy of 97%.
On the
train set. But do you think this accuracy is not correct? Because we have.
No, I'll tell you why we did that. No, we did subsequently testing also we did. Look at the line, we have done on testing also. Okay, why did I do the evaluation on training and testing? Let me tell you this, okay? With that we'll wind up. This is a very important point, and you should learn this trick now itself, and if you reflect all these things in your projects, it'll be good. Oh, there it is. Okay. Remember we talked about overfit, underfit? Okay. What is underfit? How do you define underfit? Huh? Sorry? Loosely coupled with less dimension. Straight line, curve line, what the hell, hey boss? What is going on? Using what? I want to reach a sweet spot. On the left side is low, underfit. On the right side is overfit. But how will it know whether a model is underfit or overfit? Okay. Guys, let's. Very good, thank you. Huh? Hey, no, enough. Underfit is that case where in training set accuracy is very high. Okay, I'm sorry, accuracy is very low, and in test set also accuracy is very low. Overfit is that case where in training accuracy is very high and testing accuracy is very low. All right, right fit, this is overfit. Right fit is that case where training accuracy is equal to, more or less equal to, test accuracy. All right. So if I plot a graph of errors, okay, and this is my complexity, then you will see that my training error comes to 0. Especially decision tree will give you training error 0. But this is my training error. I call it training error, TRAINING error. As my complexity increases, training error comes to 0. But you will see that this is my complexity. Okay, I'm increasing complexity in this direction. You will see that the test error is usually higher than the training error. It also comes down, but after some time it deviates back up. You'll notice that the test error also comes down to some point. After that it backs up, it peaks up. This difference, okay, this difference where the training error starts deviating back up, you should stop here. Below this it's underfit, above this it's overfit. In this situation, your model has absorbed all the noise in the training set and become very complex. And when you take that model on the test data, it bombs. Error is very high on test data. Okay, so this point is what you want to check. So whenever you build model, run the model both on training set and test set. If on training set and test set, training is 80% accuracy, test set is 60% accuracy, you are in this region. If training set and test set, both of them are similar to each other with very few difference here and there, then you are probably in this region. Training is also poor, testing is also poor, you are in this region, underfit region. Oof. So much to discuss. I know it becomes a bit of overwhelming with so much of information coming in such a short span of time. It'll take time, don't worry about it. Take time, take your own time to sink all this in and keep practicing on the UCI datasets. But don't get miscarried by the UCI datasets, as Birendra pointed out. In reality, you'll never get such datasets readily available. Never. If you get, you have to suspect it. Okay? That reality will hit you when you do the capstone project itself. The idea is to teach you that reality. All right, so I'm going to stop here. I'm done for the day. Any questions, feel free to shoot. We're stopping a bit early today, but yeah, that's, yes.
You explain the pair plot and what are the inferences we can do?
Pair plot? Yeah, sure, why not? We can do that. For this data set? Okay.
Actually, I have done this problem based on that
Scores have gone down, right? Overall, what is accuracy?
77.
Overall accuracy. Yeah, that is what 76.
Overall 74, the training set is 74.
That's okay. 74, 76, that means it's an underfit region. Both of them are very close to each other. And class level accuracy, diabetes class, recall, what is the recall? Hey, diabetics class, 88. 62 for diabetic class is 62. 55% and 62% is a big jump actually. It's a big jump. So for diabetic class, this Naïve is doing well because, can you tell me why Naïve is doing well for the diabetic class?
You told multiple, if it's overlapping, maybe the different attributes can be
Linearly scaled.
Weaker or weaker will go.
In diabetic class, in PIMA diabetes data set, you notice that there were 3 attributes on which there was a very small separation between orange and the blue on the 3 dimensions. Those weak predictors are helping the Naïve algorithm over there. Right? So the lesson that we have from this is, which we'll revisit tomorrow anyway, given data set and given problem statement, we never rely on one single algorithm. We always build multiple models. Each model might be different algorithm, and then we average out. That concept is called stacking. If you use the same algorithm multiple instances, that we call ensemble. So in production, we always put an ensemble or a stack, and the ensemble or a stack will give you a much more reliable result than individual instances will. Okay, let's move on. So let's see this pair plot. There you go. For always first look at the diagonals. Okay. In the diagonals, the first column is the category, the target column. So we can ignore this. This is category of the 3 cultivators, people who cultivate. The next column is the alcohol. Look at the diagonals. This is alcohol versus alcohol. So it makes no sense to give you scatter plot here. So instead, they have given you density distribution on the alcohol dimension. Since we have used this hue color, which means give me separate colors for separate classes, it's showing you the 3 classes. And what is coming out of this is, between classes there is overlap. But fortunately, the central values of these classes, they are not overlapping. No, this is alcohol versus alcohol. This is just distribution of the classes on alcohol, univariate. This analysis is univariate analysis. It's not comparing the dimensions. So it's giving you a distribution of cultivators from class 1, class 2, class 3 on this dimension. How the values of alcohol for class 1 is distributed, how it is for class 2, how it is for class 3. So what this is telling us is the alcohol dimension can be used to separate out the 3 classes. Okay, go to the next one. If you observe carefully, malic acid, what it's saying is the class 1 is distributed like this, the class 1 malic acids are distributed like this, class 2 malic acids are distributed like this, and class 3 is the green one. What we are seeing is outliers here. For the blue class, on this particular dimension, there seem to be outliers. You see a small bulge over here. Similarly for orange also we are seeing bulge. The problem we are seeing for the green one, there seems to be huge range on both sides. Yeah. So green one also seems to be having some extreme values on both sides. That's why the distribution itself is stretched out. So I have to go back to the records and see on this malic acid for each class, what is the problem? What are these outliers and need to deal with it? But right now, in the raw form, the green stands out separately from the orange and the blue. but the orange and the blue class are overlapping. So this dimension may be very useful in separating out greens, but may not be very good in separating out orange and blues. This dimension is your ash, is relatively the most useless dimension in this set.
If you have the outlier, suppose if you take the outlier, so you have very less spread. It means that it's a very good predictor for the blue, this data.
No, the predictive power base is a function of how cleanly these separate out the distributions. The predictive power of a dimension is a function of how cleanly these distributions are separate out. Suppose there was no blue class. This is a very good dimension to separate orange from the green. If suppose there was no green class, this is a weak predictor for orange and blue. This ash, it's a very weak predictor for all three of them. Okay. This alkalinity, if you see, if you look at, if suppose the blue class was not there, then we are in prima diabetes case. But at least it's a good separator for green and blue, right? So individual dimensions may be weak predictors, but when I put them together, they might be able to segregate the three classes properly. And that is what is happening in the data set. You asked the question, right? How to interpret this? That's what we're doing. The scatter plot makes no sense because we are not building any linear models here. Okay. So scatter plot I'm not referring. So diagonals is important for us. Any other question?
Based on this, we can drop the variables which are less important, right?
100%. So, but maybe by dropping that ash dimension and reducing the cursive dimensionality, I might be able to get more than 96%.
So if you drop the ash and again reason the volume,
I don't know. I've never done that, but you should try. Maybe you will get it. Handling the outliers might help you in classifying, because outliers, hey guys, all of you this side please. All of you this side. This is a Gaussian Naïve base. Gaussian Naïve base expects your data to be distributed like this. But wherever your data distributed like this, if you handle these outliers, you might get better results, right? So if you handle the outliers, both logistic and Naïve base will give you better results. Because outliers increase log loss in your logistic. So if you handle outliers, both logistic and Naïve base will give you good results.
But if the cost will come after like one standard
Treat it means? You're talking about outliers. Okay. Don't remove the outlier. Don't drop the records as much as possible. Unless you're lucky guy, you're given terabytes of data. Right? So usually you'll find yourself in a situation where we don't have the luxury of dropping the records.
But in case of breast cancer and all, we don't have a cell radius. If we replace it with median values or something, that's domain specific.
You have to take, yes, good point. You have to have the domain expert with you to tell you whether calculating the radius is prone to error or the perimeter is prone to error. Right? Because there's a strong relationship between perimeter and radius. That's why you're saying that. So it depends on the domain expertise you have. All right. Okay. There's one point which I wanted to say. Okay. This is called data leaks, and guys, with this I'm going to stop. I'll not go beyond this. Be careful about data leaks. I'll tell you what data leaks is. In your exams, if the question paper gets leaked out, obviously we'll score very high. Right? But we might not have the real knowledge with us. Same thing can happen in modeling. So in modeling, we break our data into training set, test set, right? and we build our model, model dot fit. We do this using training data. There are various ways in which the test data can leak into the fit function. One of the simplest way you can do this mistake is where you first take the data, you convert this data into z-score, and then you split this data into training set, test set, build your model on this. Why? Because z-score is xi minus x bar by standard deviation. Xi minus x bar by standard deviation is a z-score. This standard deviation is a result of all the records put together. Right? Now, when I break this data into z-score data into this, the test data has already been influenced by the training set. But the test data in no way should have been influenced by the training set. They are not independent of each other. This is a very common source of data leaks. In the classroom, it's okay, but you cannot do this in your projects. Then what will happen is, your model will perform well on test, but it will bomb in production. That is one very common way of data leaks. So whenever you do transformation of your data from raw to this, if the transformation involves all records put together to find your standard deviation, something of that sort, don't do that. Always break your data into training set, test set first, then do the transformations.
I think we did this for this.
Which one?
First Python notebook which we did.
We'll do this mistake in all the Python notebooks. But you please be aware of this, don't do this in your projects. The second thing I'll tell. Second problem statement is, we talked about one-hot coding. We talked about one-hot coding, right? Look at this. You have in your data set a gender column which has male, 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 females, females, okay, males. Always convert the one-hot coding first so that it becomes gender male, gender female. This will become 10 10 10 0 0 1 0 1 0 1 1 0 1 0. Okay, all of you got it? Then you break your data into training set, test set. This is okay. Training, test. The reason why this is okay is this record has not been influenced by any other records. The records don't influence each other. The transformation of records from here to here is independent of other records. So this is okay. Okay. If you do this transformation after breaking your data into training set, test set. I told you in z-score, you first break your data into training set, test set. Okay. Then first do z-score on training, then do z-score on testing separately. If you do this one-hot coding after breaking your data into training set, test set. Now I break this into training set, test set. What's going to happen is, in your training set, you're going to have only one column, GM, 1 1 1. In your test data, you're going to have two columns, GM and GF. This will be 0 1 0 1 1 0. So your training data and your test data will not match in terms of the attributes. So whenever you're doing transformation, if the transformation is something which is done record-wise, do it first, then break your data into training set, test set, especially one-hot coding. Otherwise, you'll end up in runtime problems. If you're doing any transformation which involves all the records put together, like calculating standard deviations, then first split it, then transform it. Otherwise, your data will leak.
Here, number of observations will get changed.
Second mistake is
One-
first mistake.
one
Z-score.
side will getting it to
Z-score and
Yeah.
test
Is there any effect of this? And
Catch
is there
and
any kind of bias?
Yes, yes, you are. The moment you add dimensions, you're going towards higher complexity of your models. So you're decreasing the bias error but increasing variance errors. So if you create one-hot coding out of a column where the cardinal values, the distinct values is 50, you're going to end up with 50 new columns. So imagine from lower dimensional space, you're going to such a high dimensional space, and your data points is also not very high. You'll end up with a very complex model. So you'll end up in overfit zone, variance errors.
So why we need this? We can still segregate, we can still use 0, 1 as the value for.
Algorithm will think that 1 is greater than 0.
Here, if we have three categories, A, B, C, and we do level encoding first. So it will convert to 1, 2, 3. In this case, it might think that C is a higher priority than C.
It will.
So what will do? It will do one.
Yes.
Now it will convert to 0, 0, 1, 0, 1, 0 as per the sequence. So in this case, if we drop one of the variables, the variance will also decrease, and we can predict that if it's 0, 0, then maybe that variable will be 1. So we can use that way also to reduce.
Yeah. Okay. One last point. Last test point. This we have been saying since last 3 points. Whenever you create one-hot coding, for example, in this case, you are creating collinear columns. Columns which influence each other. The presence of 0 here tells me that this column will be 1. So I'm able to predict the value of the other column based on this column. So you're introducing collinearity over here. To address this collinearity problem, when you create one-hot coding, we might drop one of the columns. So 0 means male, 1 means female. So I get that information from here itself. I don't need this. So when you do one-hot coding, you're introducing multicollinearity. When you bring multicollinearity, you know what problems exist, what problems happen, you know that. So we might have to drop some of these one-hot coding columns to remove the multicollinearity. We do that.
Again, it has 0, 1. Again, same issue. 1 is.
And the purpose of one-hot coding is.
One-hot coding does not introduce any order. It just stores it as a label, 0 and 1.
So we can also convert the gender column as a category column at 0.
Unfortunately, when you do that, when you use pandas data frame categorical function, it actually says that it is ordinal values. It has order in it. Discuss the steps and then we'll move on. We'll use a new data set on which I'll run KNN, regressor, then linear regressor, and we'll compare the two.
Turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.